Let's get started with simple harmonic motion. For each motion below, indicate whether the motion is periodic, simple harmonic, or both. As we're looking at this, let's be aware that if an object or a system has periodic motion, that does not mean that it's simple harmonic. But if it's simple harmonic, it is periodic. Think of a square and a rectangle. All squares, by definition, fit the definition of a rectangle, but not all rectangles are squares. So then what is periodic? Periodic means it has repeated motion in intervals of time, in equal intervals of time, meaning that its first period is always 90 minutes long. It always takes 365 days to make a year, always 24 hours in a day, that sort of thing. But simple harmonic has a restoring force. So think of changing direction. Child swinging on a playground swing, it's both, because it's changing direction as the child swings back and forth. But a CD rotating is only rotating in one direction at a constant speed. An oscillating pendulum and grandfather clock, periodic, and simple harmonic because it's rocking back and forth, it's changing direction. And then the moon going around the earth, of course, would just be periodic because it's not changing direction. Let's look at this. A pendulum bob moves closer to its equilibrium position. How does the magnitude of the restoring force change? Well, as it approaches equilibrium, the restoring force is going to be zero at equilibrium because that's where it wants to be. As it moves away from equilibrium, the restoring force gets larger and larger. So it's a direct correlation. The further you are from equilibrium, the larger the restoring force. But at equilibrium, your acceleration and your restoring force are both zero. How does the magnitude of the tangential acceleration along the direction of motion change? This is not not circular motion. So this is acceleration along the line that it's actually moving. So like the tangential velocity we had before, this is tangential acceleration. So if you're at equilibrium, tangential acceleration goes to zero because the restoring force is removed. If the force is gone, no force, no acceleration. And when you're at the spot you want to be at that equilibrium point, it's no longer accelerating. It's like, hey, I'm here. This is where I want to be. So tangential acceleration goes to zero when the pendulum bob reaches the equilibrium point. How does the magnitude of the velocity change? Velocity will be at its maximum when you're at the equilibrium position. As you're approaching equilibrium, acceleration is increasing your velocity to its maximum point when you reach equilibrium. As soon as you're at equilibrium, acceleration is gone. You're no longer speeding up. As soon as you pass equilibrium, acceleration changes direction and starts to slow you down. So you will continue to speed up until you reach equilibrium. As you pass equilibrium, you'll slow down. So velocity is at its max as the pendulum bob moves through the equilibrium point. And again, as you pass it, you'll start to slow down. As you approach it, you're speeding up. How does the magnitude of the centripetal acceleration change? Remember, centripetal acceleration is that center-seeking acceleration. This is back from circular motion and is calculated as v squared over r. Well, the radius isn't changing with a pendulum bob. That's already set by the pendulum itself, but the velocity is. So if we can get a maximum velocity, that would be maximizing the numerator of this fraction. We would be then maximizing the centripetal acceleration. Since the velocity is at its maximum at the equilibrium position, centripetal acceleration would also be at its highest magnitude. So at equilibrium, our centripetal acceleration is at its maximum because the formula is v squared over r. Max v is at equilibrium. But our tangential acceleration would be zero because our restoring force is zero. We have to keep those two things separate. It is a little confusing at the beginning. When an acrobat swinging on a trapeze reaches the equilibrium position, the net force acting along the direction of motion is zero. Why then does the acrobat swing past the equilibrium position? It's basically saying, well, if the force is removed and the acceleration isn't there, why don't they just stop instantaneously at that equilibrium position? Have you ever gone to a park and swung on a swing and you're going really fast back and forth? Why don't you just immediately stop at the bottom? Because you have velocity. That force has given you an acceleration. You have sped up. You've reached an acceleration. Just because you remove the acceleration doesn't mean you're not going to maintain that velocity through the equilibrium. So velocity is increasing as the acrobat approaches the equilibrium position. Though net force is 0 at equilibrium, velocity is at its highest as it passes through equilibrium. And the only way to reduce or change that velocity is through acceleration, either positive or negative. And in order to have acceleration, you have to have an unbalanced force. It's just going to take a little bit longer to get this written out, so just be patient with it while we get this written out. Again, velocity is increasing as the acrobat approaches equilibrium position. Though net force is 0, velocity is at its highest when passing through equilibrium, and this being the net force for the restoring force. Calculate the period and the frequency of a 3.5 meter long pendulum at the following locations. Well, we need a formula. If we don't already have it, the formula for a period for a pendulum is T is the period, is equal to 2 pi times the square root of L over G. L being the radius, the length of the pendulum, and G being the acceleration of gravity. On Earth, we'll use 10. Frequency being an inverse of period, so 1 over period is frequency. Remember, period is the seconds per revolution, frequency being the revolutions per second. So with the information given, the North Pole, the period is equal to 2 times pi. I'm just going to write it in as 2 times 3.14 times the square root of 3.5 divided by 9.832. That's the G they gave us for the North Pole. We put this into our calculator, and when we do, we get 3.75 seconds. That is the period. And then if we're looking for the frequency, we just simply need to do 1 over 3.75, which gets us 0.27, and the unit of frequency is hertz. Jakarta, Indonesia, where G equals 9.782 meters per second square. Again, the formula, period is equal to 2 pi times the square root of L over G, 2 times 3.14 times the square root of 3.5 divided by 9.782. Again, that 3.5 is the length of meter long pendulum that they gave us at the beginning of the question. Put that into our calculator, we get 3.76 seconds for the period. The inverse of that for frequency, 0.27 hertz. You are designing a pendulum clock on Earth to have a period of 1 second. How long should the pendulum be? Well, if our period is 1.0, we would have 1.0 is equal to 2 times 3.14, 2 times pi, times the square root of L over G. Something to note here, we're not factoring in mass of the pendulum. Can we say for this mass doesn't matter, perhaps? Let's continue the math on this. If we take the 2 times pi and we divide it to the other side, we get 0.16 is equal to the square root of L over G. If we square both sides, we get 0.0256 is equal to L over 10, L over G. And if we multiply both sides by 10, we would get 0.256 meters, because the unit we use is meters, is equal to the length of the pendulum. Number 6, you take a clock in the above problem with you to the moon, which has a mass of 7.35 times 10 to the 22nd kilograms and a radius of 1.738 times 10 to the 6 meters. What will be the period of the clock on the moon? Will it run fast or slow? Well, first we need to find out what is G, what is the acceleration of gravity for the moon. If we don't remember, G is equal to gravitational constant 6.67 times 10 to the minus 11 times the mass of the planetary body divided by the radius squared. So we got 6.67 times 10 to the minus 11 times 7.35 times 10 to the 22nd divided by the radius, and don't forget to square the radius, 1.738 times 10 to the 6 squared. When we do this math, little g for the moon would be equal to 1.62 meters per second squared. Now that we have little g, let's go back to our period formula. Our period formula being t is equal to 2 pi times the square root of L over g. Pi being 3.14, L being 0.25, and g being 1.62. 2 times pi times the square root of 0.25 divided by 1.62. Put that into a calculator, and we should get a period of 2.47 seconds. So it's going to be slower. It only took 1 second to complete a rotation in or the periodic motion on Earth, and it took 2.47 seconds, a longer period of time on the moon. Number 7, when a mass of 25 grams is attached to a certain spring, it makes 20 complete vibrations in 4 seconds. Let's kind of isolate what we have. The mass, we don't use 25 grams, we would use 0.025 kilograms. If it makes 20 complete vibrations in 4 seconds, the frequency would be 5 hertz because it's doing 5 per second. And we want to calculate the spring constant first. So we know the period is 2 pi times the square root of, for a spring now, it's going to be m over k. So mass does matter with a spring. Very similar formulas, but has their differences. So the period of a spring is 2 pi times the square root of m over k. So now we put this in our formula. If our frequency is 5, our period is 1 over 5, is equal to 2 times pi, or 2 times 3.14, times the square root of 0.025 mass in kilograms divided by k. And we can show the calculations here, but once we do the calculations all the way through, we should get 24.65 is equal to our spring constant. If allowed to come to a rest, how far will the spring be stretched from its unstretched length? So we're looking for the delta x. What is the spring's displacement from its equilibrium position? Let's draw a quick free body diagram or kind of a picture of what's going on. So here's our object hanging from a spring. The force going up would be kx, and the force going down is mg. So we have gravity going down, force of a spring going up. Well, if this object is at rest, if the spring has come to a rest, we know that mg then would be equal to k times x, or delta x in this case. It's the how far is it displaced from its happy place, its equilibrium. 0.025 is the mass times gravity 10 is equal to 24.65, the value we got from A, times delta x. Multiply by 10, divide by 24.65. That should calculate for us the displacement of the spring. Now that will be in meters. And if we want to simplify it, we can also put that into centimeters by multiplying by 100, which would be about 1.01 centimeters. Going into number 8, we're going to have a new formula again here, one that we're not going to use a lot of, but here, based on the time of the frequency and the amplitude, we're able to determine position. So let's start with number 8. A mass on an air track attached to a spring completes one oscillation every 2.4 seconds. So the period is 2.4 seconds. We know the force of a spring is k times delta x. Let's just kind of get all those things out there. I'm not sure what we're going to use, but let's see where the problem takes us. The cart is released from rest at a distance of 0.1 from its equilibrium position. So the amplitude, capital A amplitude, would be 0.1. That's how far it's going to be away from equilibrium. Think of calm water being the equilibrium position, and then when waves start coming in, when the wave goes up above its calm water position, that would be the amplitude. So the amplitude is 0.1 meters, and then the change in position would be 2 amplitudes. So the water can go above its equilibrium position, but it also can go below. So the total displacement, maximum displacement, would be 2 amplitude as far as where it's going or how far is it moving. Now we want to do this for, at 30 seconds, what position, where is our object going to be based on this information? In order to do this, we need to put together a formula, and the formula we're going to use is that position that we can calculate is equal to the amplitude times the cosine of 2 pi times frequency times time. So any position we want to calculate, the position can be calculated based on the amplitude times cosine of 2 pi times frequency times time. Now, with cosine and sine, we've always reminded you to put the calculators in degree mode, but here we've got pi in this, so we want to be in radian mode. This will be one of the few times all year long that we're in radian mode, but you must be in radian mode to get this correct. Position x, where we are in space, is equal to the amplitude times the cosine of 2 pi times the frequency times that moment in time. How long has it been going along? And again, calculator in radian mode. So we're going to use this formula in order to calculate it. So we're looking for position at 30 seconds. X is equal to 0.1, which is the amplitude for this problem, times the cosine of 2 pi. I've been writing pi as 3.14, but you can use pi, times the frequency. Well, we know the period is 2.4, so the frequency would be 1 over 2.4, times the time. In this problem, it's 30 seconds. I'm sorry, not 30 seconds, 0.3 seconds. My apologies. The time is 0.3 seconds. It's easy to overlook. Now, when you put this in your calculator, you can absolutely type in 0.1 cosine. It opens the parentheses for us. Then we can hit 2 pi button times 2.4 x to the negative 1, because that means the inverse of 2.4, times 0.3. Close parentheses, enter. As long as we're in radian mode, that will get us a solution. So x would then equal, according to this, 0.07, and that's meters. So if we multiply by 100, we can get it in centimeters, 7.1 centimeters. Is it necessary? Not always, but when you're dealing with a lot of numbers below 0, sometimes it's easier to kind of clean it up by putting it in centimeters. Let's set up the remaining questions. Again, this is kind of repetitious, but we're going to have x equals the amplitude. Amplitude is 0.1 times the cosine of 2 pi, or 2 times 3.14, times 1 over 2.4, because that's the frequency. 1 over the period is frequency. The period was 2.4, times the time, 0.6. Just following the formula. C, x is equal to 0.1 times the cosine of 2 pi times the frequency, or 1 over the period, times the time that they gave us, 2.7. And then D, x is equal to 0.1 times the cosine of 2 pi times the frequency, which is 1 over the period, times the time, 3 seconds. We can do the math for each one of these. So B would be 0.0000796 meters. Multiply that by 100, gets a little bit cleaner, 0.00796 centimeters. C would be 0.1 cosine, automatically opens the parentheses for us, 2 times pi times 2.4 x to the negative 1 times 2.7. So the amplitude, the frequency, and the times change, but everything else stays the same. for all of these from problem to problem. For this particular problem, the only thing that's really changing is the time because the system isn't changing. Now we're just at different time points identifying where the object would be. For C, we got 0.071 meters or 7.1 centimeters. And then when we get D, we would have 0.1 cosine of 2 pi times 2.4 x to the negative 1 times 3. And that gets us 0.000398 meters. Multiply it by 100, and we get 0.0398 centimeters. For number 9, in the problem above, what is the time the cart is in the position of x is equal to negative 5 centimeters? So don't forget our formula. Let's just write it down so we have it at our axis. The position is equal to the amplitude times cosine of 2 pi times frequency times time. F is frequency, which is the inverse of period. T is time in seconds. A is amplitude. And any of the distance measurements or displacement measurements will always be in meters. Now they gave it to us in centimeters, so we need to convert this to meters. So 5 centimeters would be negative 5 centimeters is negative 0.05 meters. This is the position we're solving for time. So this is the x. So negative 0.05 is equal to 0.1, the amplitude, times cosine of 2 times 3.14 pi, times the frequency, which is the inverse of the period, so 1 over 2.4 times t. And we're simply going to solve for t. So negative 0.05 is equal to 0.1 cosine of 2 times pi times the frequency. I got 2.62 t. And then negative 0.05 is equal to the cosine of 2.62 t. So I've divided the 0.1 to the other side to get 0.5. Now I'm just going to bring cosine to the other side. So cosine to the negative 1 times negative 0.5 is equal to 2.62 t. Do the left side in my calculator. So second cosine negative 0.5 is equal to 2.094 is equal to 2.62 t. Divide both sides by 2.62 t, and I got 0.8 seconds for my time.